In this video, I would like to talk about bullet physics, collision shapes, and margins. I'll be starting with understanding and visualizing collision margins. I'll try to explain and demonstrate how collision margins can be exploited. I'll also cover convex decomposition using physics primitives and convex hulls to create high performance and highly detailed concave collision shapes. Then we'll look at some quick and easy collision margin tricks you can do with bullet physics, and I'll show you how to manually create convex decompositions while at the same time utilizing these margin tricks to create high detail concave rigid body shapes. With bullet physics, it's recommended that you always use a collision margin for active rigid bodies. Typically, you would use a small margin of 0.04. However, I'll be using a larger collision margin of 0.25 to make it more obvious for this demonstration. As you can see, collision margins sometimes manifest themselves as gaps between rigid bodies. To help us visualize these collision margins, I'll add a mesh representation of them. These play no role in the physics simulation. They're simply a visual representation of the margins themselves. So what are collision margins? When collisions occur with the margins, bullet physics uses collision handling algorithms that are computationally less expensive and more robust than the ones used to handle rigid body intersection. If you don't use any collision margins, your simulations will generally run slower and be less stable. Note that given a collision between two rigid bodies, it's okay for only one to have a margin. This means that you can use on some occasion rigid bodies without margins, but you probably want to reserve that for a static collision mesh in your scene or something like that. Now that we can visualize collision margins, I'll be going through some of the different bullet physics collision shapes to explain the differences between them. The sphere primitive is the most efficient collision shape in bullet. Interestingly, the sphere primitive is implemented as a point in space with a collision margin equal to the size of the sphere's radius. The sphere is basically all collision margin. We can actually reproduce a similar sphere using a convex hull with a margin as large as the radius. So you don't need to worry about collision margins with the sphere primitives. And of course, the equivalent convex hull sphere will be a lot less efficient than the mathematical sphere primitive. The box primitive is also an extremely efficient collision shape. For it, the collision margin is contained within the bounds of the box primitive, contrary to the convex hull, which adds the collision margin to the outside of the collision shape. These both have the same dimensions, but handle collision margins differently. I'll point out that bullet physics implements some specialized or optimized primitive to primitive collision algorithms. For example, there is a specialized box-to-box primitive collision handling in bullet. You can see that the box-to-box collisions happen at the extents of the mathematical cuboids. Whereas if we're having collisions with other shapes, they may occur with the collision margin instead. This means that the box primitive collision margins should generally be kept small, and therefore we may not be able to exploit them much, but they are still required for a stable simulation. The capsule primitive, similar to the sphere, is implemented as a line with the margin equal to the capsule radius. Again, we can reproduce a similar shape using a line as a convex hull with a collision margin set to the capsule radius. As we'll see later, the capsule is useful for building compound shapes. And again, the capsule primitive is significantly more efficient than the equivalent convex hull. Like the box primitive, the cylinder primitive's margin is contained within its bounds. Again, unlike an equivalent convex hull cylinder. At this time, the cylinder primitive does not have specialized collision handling. Therefore, we should be able to exploit the collision margin, and in fact, we will do that later in this video. Contrary to the previous primitives, the cone primitive's margin is added to the extents instead of being included in them, just like the equivalent convex hull cone. Of course, again, despite the similarity, the cone primitive will be more efficient and mathematically precise than the equivalent convex hull. So for all convex hull shapes, a collision margin manifests itself as a rounded extrusion of its convex hull. The convex hull of this mesh looks something like this. So despite the sharp edges of the convex hull, a collision margin will round out those edges. This is something we can actually exploit. To understand this better, here is a convex hull with a margin of 0.25. This collision margin effectively results in a collision shape representing the beveled, extruded version of the same convex hull. Now it's important to note that this is not a scaled up version of the convex hull. If I scale this convex hull, you'll notice that it doesn't match up with the collision margin visualization. Effectively, the margin is equivalent to the individual faces being extruded by the margin amount along their normals. And these faces are joined together by a perfectly rounded edge. So to create a convex hull shape physics proxy using a margin while preserving its size, bullet physics provides the convex hull computer function that has a margin shrink option. It produces a convex hull minus the specified margin. Here's the same convex hull with a margin shrink of 0.25. This convex hull will effectively produce this beveled physics shape. The sharp edges are rounded or cut off because that is what happens when we apply a large bevel to the source convex hull. Again, this is with a margin of 0.25. With a smaller convex hull margin shrink, 0.06 in this case, we end up with a nicely beveled collision shape. And we can see that the size of the original has been preserved, the only difference being the beveling. So this is what I'm proposing. that we can exploit the robustness of collision margins to get high performance, high resolution bevel collision shapes using low resolution convex hulls. Collision margins effectively give us perfect physics shape beveling for free. So if you have a high resolution mesh, for example, one that is a smooth subdivision surface, you don't want to use it as a physics triangle mesh or even as a source for a convex hull, because you'll get very poor performance. What you want to do is create a decimated convex hull shrunk by the amount of a reasonable margin. This shrunken convex hull only has 25 vertices. With a margin of 0.06, we get a rounded collision margin that looks something like this, which effectively closely matches the original high resolution subdivision surface mesh. Only 25 vertices with a margin translates to smooth high resolution rounded edges. Bullet physics could easily simulate hundreds or thousands of these convex hulls in real time. This means we can exploit collision margins to create things like rounded cubes, or anything rounded, or basically beveled physics shapes. Again, this is a convex hull with only 8 vertices. Bullet's collision margin effectively gives us perfectly rounded edges for the same price. Same thing with the cone primitive. Bullet provides us with a mathematically perfect beveled cone using collision margins. Lots of fun to be had exploiting collision margins. I will point out one thing you do need to take into consideration. At this time, Bullet might not factor collision margins when calculating the inertia tensor. Therefore, convex hulls with large margins may not rotate properly. You can rectify this by scaling the inertia tensor relative to the margin size to correct its behavior. Okay, now on to compound rigid bodies. Compound rigid bodies are useful to create concave collision shapes out of efficient convex collision shapes. You can build compound rigid bodies many different ways. For example, here I have manually built a compound physics table shape using only box primitives to estimate the collision shape of the different table parts. A compound rigid body composed of entirely of physics primitives will be significantly more efficient and robust than a triangle mesh shape. In fact, this box primitive compound shape is going to be stable even when stacked. If we run the simulation, it's solid. Let's add a few more. Still solid. So this is a concave physics shape made out of compound box primitives. You'd be able to simulate several hundred of these in real time with Bullet because of how efficient physics primitives are. The number of shapes you can create using compound physics primitives is truly limitless. Here's just some simple examples. Using just box primitives lined up together following a path, we're able to create a sharp-edged curve, or box curve, as I've called it. You can also do a similar thing with a closed curve. Here I'm just using 8 box primitives to simulate a concave ring with sharp edges. Here we have the capsule primitive lined up along a curve. Compounded together, they work very well. Here we have a closed ring using just 8 capsules to simulate this shape. And back here, spiky ball, if I hide the mesh, you'll see it's simply a sphere primitive and a whole bunch of cone primitives with a margin, which means that we have rounded edges to our cones. So these compound shapes created entirely out of primitive shapes will be very efficient computationally, and you'd be able to have many of these in a scene, and they're very robust. Okay, you can also create compound shapes using convex hulls. Here I used Bullet's automated convex decomposition tool called HACD, and then I performed a margin shrink on the decimated convex hulls to approximate the smooth, rounded edges of our high-resolution mesh. Automated convex decomposition will allow you to create almost any collision shape using efficient convex hulls compounded together. As you can see, this concave mesh is well approximated using this technique. Bullet will be able to simulate a good number of complex physics shapes like this reliably. As I duplicate our shape, you'll notice that Blender is slowing down, but this is in large part due to the high resolution mesh. How will Bullet Physics handle the physics simulation? No problem. So here we have a complex concave physics shape being simulated using high performance compounded convex hull physics shapes with a collision margin, which again is providing us with smooth, rounded edges. Now, let's try a few collision margin tricks. If you recall, a sphere shape was a point with a margin and a capsule shape was a line with a margin. Let's see what happens when we use a rectangle with a margin of 0.1. Our collision shape effectively looks something like this. Okay, let's duplicate this shape. And what I'll do is I'll join them end to end in intervals of 0.4 actually on the Z. And I'm going to connect them using a constraint chain. So I'm going to run the simulation. What happens? We get sort of a rigid tape. This would probably look better as a skinned deformation of the tape mesh. But as a quick one, it works okay. It's an interesting shape. Okay, let's try something else here. Let's create a bevel cylinder. So I'm going to use a Bezier circle and I'm going to extrude it a little. I'm going to set the depth to 0.2, which will be my margin. Convert it to mesh. Clean up some of the vertices. Actually, I'll UV unwrap while I'm at it and give it a texture. So this is going to be a rigid body, and I'll give it a mass. So this is going to be a cylinder with a margin of 0.2, which is exactly what I created the mesh with as a bevel. And you'll see that instantly the physics simulation is simulating the bevel of our cylinder because it's built into there. Let's create a stack of these. And there you have a bunch of shuffleboard pucks, nicely beveled. Let's try creating a manual convex decomposition now. What I'll do is I'll use this cylinder and try to make a hollow object. So I'm going to define this as a convex hull. It's going to be compounded. I'm going to use a margin of 0.1, give it a mass. So what I need to do now is separate all these faces. So I'm going to use the edge split modifier with a 0° angle to separate all the faces. And now I'm going to separate all the faces into separate objects by using the separate by loose parts operator. And I'm going to parent all these objects together so that we have a compounded. Our physics objects is basically done now. We have a compounded physics collision shape that has a margin of 0.1. Let's create our visual mesh representation now. Now this is not the physics shape, it's just the visual mesh representation of what the physics shape we just created. So the bevel is going to be equal to 0.1, the same as what we set our margin. And there we have it. So this is going to be non-collision mesh because it's our display mesh. Let's convert it to a mesh. Clean up some of the vertices. Let's unwrap the UV and assign it a texture while we're at it. And we're going to have to parent this to our compounded cylinder. And now we're done. That was it. Took a few seconds. There's our physics compounded object, and there's what it looks, the physics representation of the collision shape with the margin. Let's try something a little bit more complicated now. We're going to start with a Bezier curve and we'll modify it. So I'm going to extrude that just a bit to give it some thickness. And well, actually that's going to be our physics shape. So let's duplicate that. And that duplicate we'll work on that later as our visual mesh representation, but for now I'll go back and complete our physics shape. So I'm going to convert that to a mesh, and again we have a bunch of faces. We're going to make this a rigid body. It's convex hull again with 0.1 margin, and it's going to be compounded. And just like before, what we're going to do is we're going to separate all the faces, first using the edge split modifier at 0 degrees. And then we're going to separate all the faces into separate objects by using the separate by loose parts. And we're going to parent them all together into one big compounded object. Now let's work on our visual mesh. I'm going to increase the resolution here to make it look better. Our depth is equal to our margin. And there we go. That's what it's going to look like. So let's convert that into a mesh. Clean it up a bit. UV unwrap. And assign it a texture. And it's non-collision mesh. We're going to make it a child of our compounded physics object. So that took us a few seconds again. There's our physics compounded mesh, and that's what the collision shape's going to look like. A visual representation of it. How does it work? Well, let's move this over to the right and see how it behaves with other objects. How the collisions will behave. Actually, let's duplicate this as well. Put a few of them together. See how the collisions are handled. Because this is all collision margin basically. We have 2D objects in there. And there you go, it's working well. See, it took us 2 seconds to set up a manual convex decomposition using a margin trick again. I also tried a half circle, or half sphere, sorry, and separated all the faces. Now this is fairly high resolution, but I'm trying the same thing here as a margin trick, and this is what it gave me. And it's actually a bowl that works quite well. So that's it.